Welcome back to the C programming language in action. In this module, we're going to learn about variables. Without variables, no program can do much of anything. Variables let our programs represent, manipulate, and communicate information. This might be information relevant to the users of our programs, or just information used internally to hold our programs together and give them life. In programming terms, state. Although we covered variables briefly in the language tour earlier in this course, here we're going to look at them in much closer detail, from the point of declaration, how objects come to life, and how long they survive. Let's jump right in. We're going to examine more closely how variables are declared, what your options are, and what the trade-offs might be. As with functions, variables need to be declared before they may be used. You can get yourself into all kinds of trouble declaring variables in various ways, so I'll stick to what I'd call the safe and recommended way of declaring variables. We've already declared variables in this course. A variable has a type, and it has a name, and an optional initializer. The initializer is optional, but you're very much encouraged to include an initializer. Without an initializer, the variable has an undefined or unpredictable value initially. This might be fine, but it is a common source of bugs, and if you forget to initialize the variable, and it accidentally works some of the time, even most of the time, it can also lead to various exploits which you really don't want. Older C compilers would not allow variable declarations and other statements to be mixed. You had to declare all variables up front. So this would not be allowed. All of a function's local variables needed to be declared immediately following the left curly brace of a function or some other nested block of code, like this. But fortunately, modern C compilers do support this style, which C++ introduced many years ago. This means there's practically no reason not to initialize variables, as you can simply initialize variables as soon as you need them and know what values they might need to hold from the get-go. If you were simply declaring a variable to be populated by some other function, you may not need to initialize it, but at least in this case you can define it right before it's populated, reducing the risk of uninitialized data floating around your program. As I illustrated before, you can declare multiple variables in one declaration. But this is problematic. I can initialize them individually, and that's fine, but this, well, this will compile, but often confuses human readers into thinking that both variables will have the same initial value, when in fact hens will be uninitialized and only eggs will be 6. But it's problematic for other reasons to do with pointers, but I'll get back to that later on. Better to use separate statements to declare each variable. It takes a bit more space, but space is cheap, and comprehension is far more valuable. In this segment, we're going to consider the scope, lifetime, and visibility of your variables. Thus far, we've only considered local, sometimes called automatic, variables that are declared within functions. These variables exist for the lifetime of the function in which they've been declared. They come into existence, their storage is provided anew every time the function is called, and they cease to exist when the function returns. They are also only visible, directly at least, from within the same function. Let me illustrate. Let's take these variables and move them into a new function. I'll initialize the one but leave the other uninitialized. Next, I'll increment both. This will add 1 to each variable's value. So eggs will be 5, and hens will be 1 more than whatever it defaulted to, which, as I've mentioned, is undefined or unpredictable. And I'll just use printf so we can see what this looks like. Okay, now let's call this function a few times from within main. Great. Now what do you suppose this program will print out? Think about it for a moment before carrying on. Let's take a look. So right away, the compiler picks up the fact that we're using an uninitialized variable, which is undoubtedly a bug. But it was only a warning, so let's see what happens. So that's interesting. The hens variable, which we left uninitialized, just picks up its initial value from whatever garbage was left on the stack when the function happened to be called. Since we called the function consecutively, subsequent calls to the run function happens to find the previous value, so it appears as if it retains its value, but that's just a coincidence. The eggs variable is unaffected by the garbage on the stack, since we're careful to initialize the variable upon declaration. But this coincidence of having the variable seemingly remember its value from one call of the run function to the next seems like it could come in handy. This would never work as is, but fortunately, there's a way to make it work reliably. We'll look at that next. In this segment, I'm going to show you how to create local variables with static duration. In the previous segment, we saw how uninitialized variables, while dangerous, had an interesting property by chance that might come in handy. Fortunately, the C and C++ compilers provide a way for variables to retain their values across function calls. We just need to tell the compiler that we'd like a particular variable to remain in existence, sometimes called static duration. This means that the storage for the variable is provided or allocated when the program starts and remains stable for the lifetime of the application, rather than coming and going each time the function is called. Again, this has the effect of ensuring that the variable reliably retains its value between calls to the function. The compiler will also default initialize the variable to 0 unless you provide your own initializer. Let's give it a try. This time there's no compiler warning about uninitialized local variables. Indeed, even though it may not look like it, this variable is in fact initialized to 0. The result only coincidentally looks the same as before. We can confirm this by trampling on the stack between calls to the run function. So that's a meaningless function that just writes some values to the stack. We can then call it prior to each run function call to overwrite whatever might be lingering on the stack. Now, if we compile this again, there are some warnings about those unused variables in the trample function, which we'll just ignore. And then if we run this program, the results continue to be predictable. The hens variable is initialized to 0 since it's a static variable and this function is unaffected by whatever garbage remained on the stack. But if we now remove the static declaration, and try it again, we're back in unpredictable land. This time we can clearly see that the uninitialized variable picked up some dirt from the stack as its initial value. It grabbed the 1, 2, 3 that was previously written to the stack and incremented it. Of course, we don't need to rely on default initialization for static variables. We can also initialize the static variable with a certain value, and that value will apply the first time the function is called. This is one of those areas where C and C++ are not quite on the same page, unfortunately. So far, everyone's happy. C requires that the static variables be initialized with a constant expression. In other words, an expression whose value is known at compile time, while C++ does not have such a requirement. Let's see what this looks like. Great. So here we can see that both variables have an initial value of 4. But the first is initialized only once and then retains its value. The second is not static, so it's reinitialized every time the function is called. But now, what if we swap things around a bit? If we made the eggs variable static and initialized it with a non-static hens variable? Does that even make sense? Let's see. I'll just get rid of the trample. And let's take a look. Well, the C compiler is not interested in compiling this code. It requires the initializer for a static declaration to be const. It does not consider the hens variable a constant expression, which indeed it is not. But what happens if we compile this as C++? Ah, interesting. Now it compiles without complaint. So, the idea of initializing a static local variable with the non-constant expressions seems like it could be dangerous, and at least somewhat unpredictable, so C doesn't allow it. At the same time, it can sometimes be handy, and there's really no reason to forbid it, so C++ does in fact allow it. C++ will initialize the static variable with the initializer the first time the function is called, and skip this initialization on subsequent calls. To be fair, this has some complications for compilers when it comes to multi-threaded applications, but that's a separate issue. In this segment, I want to show you how you might share static variables with static duration across functions. So we've established how static local variables work and how they might be handy in retaining state across function calls. But realistically, you might want to share state across different functions that need to operate on the same variables. One way to do this is with static variables declared at file scope. So within the context of the file rather than a particular function. That way the declaration is visible to any and all subsequent functions. Again, this will be default initialized to 0 unless you provide your own initializer. We can now write different functions that will share the static variable. We can write an up function, and a down function. We can now call these functions from our main function. At the end of this sequence, we should have 15 eggs. Let's check. Wonderful. Now, you might be tempted to remove the static declaration from this variable but I'd advise against it. At file scopes such as this, static variables are only accessible from within the same source file. But if you remove this static, it's possible that other declarations in completely separate source files will share the storage for a variable with the same name. This might sound convenient, but it quickly becomes unmanageable and should be avoided. I'm going to show you some of the basic types or data types that are available in C. C only has a small selection of types, and some variations on those types, from which you can then build more elaborate types. We've already looked at some, such as int for integers and float for floating point or real numbers. And there's not much more. There's also a double precision version of float called double, and a type used for bytes or characters. These types describe what may be stored in each variable and what operations may be performed. There are also various qualifiers that you can use to adorn these types. How much space is required for each of these variables? One way is to check for yourself, and I'll show you how in a moment. But first, some of the variations. How about an unsigned integer? Integers are by default signed, so this gives you a little more storage when the sign is not required. There are also short and long versions of int. Short and long provide different storage where possible and depending on the compiler and platform. Regular int usually maps to the natural size of a word on a particular machine, so for 32-bit machines, int is usually 32 bits. Short is often 16, and long is also just 32 bits, although in some machines it might be 64 bits. All of these unsigned, short, long integers can be abbreviated by removing the int. This is just a shorthand and makes no difference to the compiler. Unfortunately, char or characters may also be signed or unsigned. That's not so much a problem. The problem is that there's not a whole lot of consensus on whether plain old characters are signed or not. The best thing to do is use plain old char for characters and unsigned char when you need to represent bytes. For that, we can use what's known as a type diff or type definition. In practice, it's often useful and even essential that we know the exact size of the various types. We might need a 32-bit variable or an 8-bit variable for some buffer or network packet. To determine these sizes, we can use the size of operator. Let's print out one of these variables along with its size in bytes. Size of itself can cause some confusion, since it returns a value whose size is large enough to hold a pointer value. But the fundamental types are never going to be that big, so I'm just casting the result to an integer for simplicity. That's this int here in brackets. Now we could do this for all the types. We could then add type diffs, as we did here for byte, once we figured out all of the sizes. Fortunately, this has already been done for us in the C standard library. Still, let's just give this a quick try. Now, since we declared a bunch of variables but never used them, the compiler is warning about these unreferenced variables. That's usually a bug, so that's good, but occasionally you may need to silence certain warnings, so let me show you how to do that here. You can use the WD option, which stands for Warning Disable, and the appropriate warning number, 4189 in this case. That's better. Alright, let's see what it prints out. So, the value of the variable was 123, and its size in bytes, the amount of storage required for this variable is 4, or 4 bytes. 4 times 8 is 32, so that's a 32-bit integer, which tells us it's likely that the program is running in a 32-bit address space, which it is. Okay, that's enough about variables for the time being. Obviously, we're going to be using variables throughout this course, so the ideas presented in this module will be reinforced and elaborated on as we progress and write code. But it's helpful to have some foundational understanding of variables before we proceed. The main thing to remember is that variables must be declared before they are used. This tells you and the compiler what operations are permitted and what sorts of values those variables may store on your behalf. A variable declaration has a type, such as int or float, followed by the variable's name, and ending in an optional but recommended initializer. For example, here's a variable called chickens whose type is int and whose initial value is 10. Okay, it's time to move on. With a basic understanding of the fundamental types, how to declare and use variables, it's time to look at structures, the ability to collect or group a number of variables together, and give them names to represent more interesting types. That's up next.